So for this section, we're going to be talking about verifying identities. So verifying identities is basically proving that one type of expression involving trigonometric functions is equal to another one. And to build up to that, we're going to go ahead and start with the following problem. We want to write 1 plus cotangent squared theta over 1 minus cosecant squared theta in terms of secant only. So this will help us get into the habit of understanding how to rework these problems into a different form. And the way we're going to be doing this is using identities that we've introduced previously. So to start off with, 1 plus cotangent squared theta. We've come across this before. 1 plus cotangent squared theta is equal to cosecant squared theta. This is one of our trig identities. In fact, let me be more clear on that. This is one of our Pythagorean identities. So there are 3 Pythagorean identities that come up all the time when you're verifying identities. And this is one of the main ones. So we're going to use this formula to rewrite 1 plus cotangent squared theta as just cosecant squared theta. So when we do that, we get cosecant squared theta over 1 minus cosecant squared theta. And a very common mistake at this point would be to cancel out these cosecant squared thetas, but remember you can only cancel out when you are multiplying or dividing only, but because we have this subtraction we cannot do that. So the next thing that we can do from here is take a look at this 1 minus cosecant squared theta. Is there a way that we could go back to this Pythagorean identity and rework it to look like this? And there is. So we're going to go ahead and copy this down again. 1 plus cotangent squared theta equals cosecant squared theta, our Pythagorean identity. If we were to subtract cosecant squared theta from each side of this Pythagorean identity, then we would have 1 minus cosecant squared theta, which is exactly what we're looking for. Then it would be plus cotangent squared theta equals 0. So since we just want the 1 minus cosecant squared theta, we need to get rid of this cotangent squared theta, so we're going to subtract cotangent squared theta from each side of the equation, which gives us 1 minus cosecant squared theta equals negative cotangent squared theta. This is one of our Pythagorean identities, just rewritten to look a different way. So now going back to the last step we had in our problem, that's a weird arrow, sorry. We had 1 minus cosecant squared theta. Now we know we could rewrite that as negative cotangent squared theta, since this came from one of our Pythagorean identities, which means it must always be true. So our problem can now become cosecant squared theta over negative cotangent squared theta. And now we could just do some quick manipulation with this by changing these to their values in terms of sine and cosine. So cosecant squared theta is the same thing as 1 over sine squared theta. And negative cotangent squared theta is the same thing as negative cosine squared theta over sine squared theta. What do you notice about each of these inner fractions of the larger fraction overall? Well, they both have a denominator of sine squared theta. So if we were to multiply the numerator by sine squared theta and the denominator by sine squared theta, that would cancel out the sine squared theta from each of the denominators, leaving us with 1 over 1 in the numerator, which is just 1, over negative cosine squared theta over 1, or just negative cosine squared theta. And I apologize if this is getting a bit cramped here, but we're on our last step at this point. And finally, 1 over negative cosine squared theta. Well, remember, 1 over cosine is secant. So we can change this to negative secant squared theta. And that gives us exactly what we were looking for. We have rewritten 1 plus cotangent squared theta over 1 minus cosecant squared theta in terms of secant only. It can be expressed as negative secant squared theta. This is essentially the process that verifying identities will follow. We reworked the entire problem to look like something else without adding or subtracting or multiplying anything to the problem. Now you might look at these steps here in the Pythagorean identity where we added or subtracted from each side. But it's perfectly okay to do that. It's just in the actual problem itself, the 1 plus cotangent squared over 1 minus cosecant squared, that we can't add or subtract anything to it. And we'll get more into that in a few moments. From here, I want to go ahead and try another problem. We want to write sine theta in terms of cotangent theta. We'll go ahead and do this one together as well because it's a little bit difficult to ask you to try this on your own at this point. So we want to write sine of theta in terms of cotangent theta. And the way we're going to do that is, again, looking at our 3 Pythagorean identities. We want to pick one of them that will allow us to do this. And the one that we want to use is actually the same one that we used in the previous problem. 1 plus cotangent squared theta is equal to cosecant squared theta. And why is it that we would want to pick that? If you look at your Pythagorean identities, if you pull up a sheet from Google or any one in particular, you have sine squared plus cosine squared. So sine squared theta plus cosine squared theta equals 1. 1 plus tangent squared theta equals secant squared theta. And 1 plus cotangent squared theta equals cosecant squared theta. So which of those 3 would help us write sine in terms of cotangent? Well, it ends up being this one because this is the only one that deals with cotangent and a form of sine. Remember, cosecant is the reciprocal of sine. So we can start reworking this to become sine of theta equals some value. The way we can do that is, notice cosecant again is the reciprocal of sine, so let's rewrite it like that. We have 1 plus cotangent squared theta equals 1 over sine squared theta. We've taken the reciprocal to change this to sine instead of cosecant. And now from here we can do a pretty neat trick, which says we're just going to take 1 plus cotangent squared and put it over 1, since that doesn't change the problem. And whenever you have 2 fractions equal to each other, you can just take the reciprocal and set those equal to each other, meaning this becomes 1 over 1 plus cotangent squared theta equals sine squared theta over 1. You're only allowed to do this when taking the reciprocal won't cause division by 0, but this is just a quick way to go about simplifying the problem. And now that we have this, we don't really need this divided by 1 here, so I'll go ahead and erase it. So we have sine squared theta equals 1 over cotangent squared theta. And how do we get sine from here? Well, we just take the square root of each side to get sine of theta equals plus or minus, because we took the square root of each side, the square root of 1 over 1 plus cotangent squared theta. And we're just going to leave it just like that. We don't need to worry about rationalizing this or, getting rid of the square root in the denominator or anything like that. All we really cared about in this problem was just getting sine of theta in terms of cotangent of theta only, which is exactly what we did here. So we'll leave it just like this. Alright, so now we can go ahead and get to verifying these identities. So the process for verifying identities is not an exact one. It's basically a suggestion. Look at it in the following way, and generally this is the process you'll want to follow. But it's not as simple as if you have x plus 2 equals 5, then subtract 2 from each side. It doesn't work out that simply. It's just practice this a bunch and look for the common things that occur every now and again. So, we have the process to verify identities. The first step is to choose the more complicated side. So, if you look at the following verify the identity example, you have something equals something else. You're verifying that this is true. You're proving it's true. You're only allowed to work with one side, so you can't add or subtract things from each side. You can't multiply something to each side, so you can't multiply 2 to each side of the equation. That isn't proving that this side equals this side. You're only allowed to take one of the sides and start reworking it to look like the original other side. The only time where this isn't true is if the identity problem says you can use both sides. But that is very rare. Okay, just to add one more note though, if you have a fraction on one side, it's perfectly okay to multiply the numerator and denominator by a number, because it's like you're multiplying by 1. You're not changing the problem. But you cannot multiply this side by 3 and this side by 3. Only work with one side of the equal sign. Okay, so from there, the next thing you should look out for when you pick the more complicated side is you want to check for Pythagorean identities. Generally, those are the first thing you should look for. From there, you should check if you can factor or multiply anything. And then, this is the step where things get a little bit odd. If you're given 1 plus any of your trig functions, so 1 plus sine, 1 plus cosine, or 1 minus sine, 1 minus cosine, and so on, then you need to multiply by the conjugate. So if you're given 1 plus cosine x, multiply by 1 minus cosine x to the numerator and denominator of that value. So, for instance, if we have 1 plus cosine x, you're going to put this over 1 and multiply by 1 minus cosine x over 1 minus cosine x. We're multiplying it only to this fraction, to the top and bottom, so it's still okay with our verifying process. And we do this because in the numerator you would end up getting 1 minus cosine squared x, which allows you to start using Pythagorean identities to manipulate the problem. This is one of the rarer things that comes up, but it does come up every now and again, so it is worth being aware of it. And finally, from here, if all of these fail, your last go-to is basically change everything in the problem to just sine and cosine, because maybe something will look like it'll cancel out. Alright, so going to this example, we want to verify that cotangent theta plus 1 equals cosecant theta times cosine theta plus sine theta. So, we're only allowed to work with one side here. So which one looks more complicated? Well, the right side looks a lot more complicated. Notice the left side only has one trig function. This side has 3 trig functions. So generally you're going to want to pick the side with more trig functions to work with. Always remember, it's easier to turn multiple trig functions into one than it is to turn one trig function into multiple trig functions. Okay, so with that in mind, how can we go about this? Well, we don't have any Pythagorean identities, so we should check if we could factor or multiply. We can multiply. We can distribute cosecant theta, which gives us cosecant theta times cosine theta plus cosecant theta times sine theta. And from here, cosecant theta times sine theta, well, those are reciprocals, and whenever you multiply reciprocals, the result is 1. So we have cosecant theta times cosine theta plus 1. Now notice this is very close to what we're looking for. If we can find a way to change cosecant theta times cosine theta to cotangent theta, then we already have the plus 1. So what can we do with this? Well, it's not very apparent from here, so why don't we try our last step? Change everything to sine and cosine. Cosecant theta is the same thing as 1 over sine theta times this cosine theta plus 1. And now cosine theta times 1 over sine theta, we can put cosine theta over 1 and multiply straight across to get cosine theta over sine theta plus 1. And with that, we know that cosine theta over sine theta is cotangent theta. So we have the value we're looking for. Cotangent theta is exactly what we were looking for. So we just put in a filled square. This basically means QED. It means that the proof is done. So we have verified the identity. Okay, let's go ahead and try another one of these. We want to verify that tangent squared x times 1 plus cotangent squared x equals 1 over 1 minus sine squared x. In this problem, picking the more complicated side is a bit tricky because both of these sides are quite complicated. But remember what I said in the previous problem? With this side, you have 2 trig functions. With this side, you have 1. It's easier to condense trig functions down into 1 than it is to change one trig function into multiple trig functions. So we should probably pick the left side here. So what should we start off with? Well, we have tangent squared x times 1 plus cotangent squared x. 1 plus cotangent squared x is one of our Pythagorean identities. we know that 1 plus cotangent squared x is equal to cosecant squared x. And whenever you use one of your Pythagorean identities, you should make a note of it off to the side of the step that you used it in the problem, just to show your work that you are proving this is true. So we're going to go ahead and substitute that into the problem. We get tangent squared x times cosecant squared x. And now from here, we can go ahead and change everything to just sine and cosine since there isn't too much left to do here. So when we do that, we get sine squared x over cosine squared x instead of tangent squared x times 1 over sine squared x instead of cosecant squared x. And now notice what happened here. The sine squareds will cancel out since we have one in the top and one in the bottom and we're multiplying, which leaves us with just 1 over cosine squared x. And now we're getting very close to what we were looking for because, remember, we needed to find 1 over 1 minus sine squared x. Right now we have 1 over cosine squared x. So how could we go about this? Well, we're going to look at our Pythagorean identities again. Note that our first Pythagorean identity is sine squared x plus cosine squared x equals 1. And if we want to solve for cosine squared x, then we would just subtract sine squared x from each side of the Pythagorean identity. Remember, you cannot do this in the problem that you're verifying, but it's perfectly okay to add or subtract from each side in the Pythagorean identity itself. So when we do this, we get cosine squared x equals 1 minus sine squared x. So substituting that in, we get 1 over cosine squared x is now 1 minus sine squared x. And that's exactly what we were looking for. We just verified our identity. It's equal to 1 over 1 minus sine squared x. And that's it. We put in our filled square to say that the proof is finished. All right, continuing on with this, we now have another example. We want to verify secant x plus tangent x over secant x minus tangent x equals 1 plus 2 sine x plus sine squared x over cosine squared x, using both sides. Now, just to be clear, you don't have to use both sides. It's just that when it says you're allowed to manipulate both sides. It'll make the problem a bit easier on you. As soon as you can show one step is equal to another step anywhere along the way, you've verified the identity. Okay, so how are we going to go about this? Well, let's go ahead and start with this left side. None of our process rules are apparent in this step, so what we should consider is changing everything to sine and cosine. So to start off with, secant x is the same thing as 1 over cosine x, plus tangent x is sine x over cosine x, over secant x is again 1 over cosine x, minus tangent x is again sine x over cosine x. And now that we've done this, we can notice that every denominator is cosine x. So if we multiply the numerator and denominator of this entire large fraction by cosine x. Again, this is perfectly okay because we're not multiplying it to both sides of the equal sign, just to the top and bottom of this fraction on the left. When we distribute this cosine x to each fraction, it's going to cancel out every denominator, leaving us with just 1 plus sine x over 1 minus sine x. Okay, from there, let's see what we can't do with the right side. So remember, if you don't have a Pythagorean identity clearly showing, then the next thing you should consider is factor or multiplying. Notice the top can be factored. It's kind of odd to look at 1 plus 2 sine x plus sine squared x and say that can be factored, but there's a method we call u substitution where we say let u equal sine of x. Then what would this problem look like? We would have 1 plus 2 sine of x is now u, plus sine squared x is now u squared. And if I asked you to factor this, you would probably say 1 plus u times 1 plus u. This is one of our perfect squares. And now that we have this factored, we can plug u's value back in to get 1 plus sine of x times 1 plus sine of x, or 1 plus sine of x quantity squared. Okay, so now that we have that factored, we can go ahead and show that on the right side. We have 1 plus sine x times 1 plus sine x over cosine squared x. And now from here, we can change cosine squared x. Notice on the left, everything's in terms of sine. So we should probably get rid of this cosine if we want to verify that the left side equals the right side. How can we do that? Well, this is where one of our Pythagorean identities comes into play. We have that sine squared x plus cosine squared x equals 1. So solving for cosine squared x, we'll subtract sine squared x from each side. Which gives us cosine squared x equals 1 minus sine squared x. And now we can go ahead and plug that in. So again, we'll copy down the numerator. And when we do this, the denominator now becomes 1 minus sine squared x. But now notice again, we have the ability to factor. 1 minus sine squared x is a difference of squares. So we can rewrite this. I'm going to go ahead and copy down the numerator again. Okay, so from here, 1 minus sine squared x can be rewritten as 1 minus sine x times 1 plus sine x. Remember, whenever you have a perfect square minus another perfect square, you just take the square root of the first term minus the square root of the second term, and then multiply it by the square root of the first term plus the square root of the second term. And now, why did we just do this? Well, notice we have a 1 plus sine of x multiplied in the numerator and denominator. We can cancel them out, leaving us with 1 plus sine of x over 1 minus sine of x. And that is exactly what we have on this side on the left. Which means the identity has been verified. We put our filled in box to note that we have proved it. Okay, last problem. At this point, we've gone through quite a few examples. I want you to take a moment, try this problem, pause the video, see if you can't verify that secant squared x times sine cubed x minus secant squared x times sine x equals negative sine x. Okay, trying this together. The first thing we should look for is our Pythagorean identities. So obviously the more complicated side here is on the left. Hopefully that's what you picked. So with that, do we have any Pythagorean identities? Well, kind of. We have a secant squared that we could rework, but what we should look to next is, can we factor or multiply? And this is the key step here. We can factor out a secant squared x times sine x from both terms that are being subtracted. And that's exactly what we're going to do. I want to be very clear here. On these verifying identity problems, there are so many ways to go about verifying an identity. So if you did a different first step, it doesn't necessarily mean it's wrong. This is just the easiest way that I've found to go about this problem, is to factor out secant squared x times sine of x. So when we do this, we get secant squared x times sine of x times, what's left here when we factor out secant squared x times sine of x? Well, the secant squared is gone, but we only took one of the three sine x's, so we're left with a sine squared x minus, over here we factored out secant squared x times sine x, so we factored the entire thing out, meaning that there's just a 1 left. Whenever you factor out the entire term, it means you divided out the entire term. Anything divided by itself is just 1. Okay, so from here, what can we do with this? Well, sine squared x minus 1 looks like one of our Pythagorean identities. So off to the side, remember sine squared x plus cosine squared x equals 1. If we subtract 1 from each side, we get sine squared x minus 1 plus cosine squared x equals 0. And now this is the value we're looking for, the sine squared x minus 1 in our problem. So to get it by itself, we'll subtract cosine squared x from each side, which gives us sine squared x minus 1 equals negative cosine squared x. Remember, every time you use these Pythagorean identities in your problem, you should always write them out, showing all of these steps. So we can now substitute in negative cosine squared x for sine squared x minus 1. And that's going to be multiplied by secant squared x times sine of x. And now notice secant squared x times cosine squared x, those are reciprocals. When you multiply them together, the result will just be 1. So they're going to cancel each other out, leaving us with just a negative times sine of x. And that is exactly what we were looking for on the right side. So this problem has been verified.